All right, here we go. So this chapter, we're going to be talking about what's called simple harmonic motion and making some connections with that and energy. All right, we're going to be focusing on one specific type of periodic motion. All right, so what is periodic motion? Periodic motion is basically motion that repeats itself at regular intervals. Okay, the specific type of periodic motion we're going to talk about is what's called simple harmonic motion. All right, so how is simple harmonic motion different from other types of periodic motion? Well, in any oscillation, so imagine a thing oscillating back and forth. So maybe it starts here, and then it goes and oscillates back and forth like this, right? Well, the idea is it's changing direction, right? Some of the time it's going this way, some of the time it's going that way. It's, it speeds up, it slows down, all right? So there has to be a force causing that change, all right? Simple harmonic motion is motion in which the restoring force, the force causing that change, is proportional to the displacement from sort of the center of its oscillation. So your restoring force is equal to negative k times x, where here's your center, and x is how far away from that center you are. Okay? This should look familiar, right? This is Hooke's law for an ideal spring, right? Okay? So k is going to be some number of newtons per meter for some, and it's always going to be positive, okay? All right, so before we get into that, a couple quick reminders. These are definitions you should know, but so just to kind of refresh your memory. So period, capital letter T, is the amount of time it takes for one full cycle, all right? It's the amount of time. And so the units we're going to use are the number of seconds per cycle, or more simply, seconds, all right? Frequency is, instead of the time for one cycle, it's the number of cycles per unit time. All right, and so the units we'll use there will be cycles per second, or more simply, hertz, abbreviated Hz. All right, and finally, this last thing, this is a little bit weird, and I think it'll make a little bit more sense once you see how the functions are written. So basically, angular frequency is the same as regular frequency, except instead of measuring it in cycles per second, we're going to measure it in radians per second. So basically what we're going to do is we're going to divide each oscillation, we're going to divide each cycle up into 2 pi radians, okay? And even though the object isn't necessarily rotating or kind of traveling in a circle, we can still kind of take this oscillation, divide it up evenly into 2 pi radians, and then convert, right? So every one cycle is 2 pi radians, and so angular frequency is the number of radians completed per unit time, all right? Notice it's similar to, but not exactly the same as angular velocity. We'll talk more about that distinction in the next video, okay? All right, and so the units for frequency are simply radians per second. All right, so some relationships you should know. Frequency and period are reciprocals. Our angular frequency is the same as frequency times 2 pi, because you're just taking each of these rotations and splitting it into 2 pi radians, all right? Or it's 2 pi is the number of radians in one rotation, divided by the time for one rotation, and that'll give you your angular frequency, okay? I just said rotation twice. I actually meant cycles or oscillations. Same idea, okay? Again, I think this omega idea will make a little bit more sense once you see how we're going to express the functions, okay? So, where do we want to go next? Let me take a look at my notes before I jump to the next slide. Okay, so what do the oscillations look like? Well, so I already referenced this idea that the restoring force is proportional to the displacement, okay, which made you think of springs. All right, so let's take a quick second and do this. Let's look at a quick simulation, okay? So I'm going to go over here, and I'm going to get rid of all of this ink from my last effort at making this video. Made one too many mistakes, and I said, you know what, I'm starting over. Okay, so here we go. So, stop, let's get rid of this. All right, so here I've got a spring, right? Okay, I'm going to take a mass, and I'm going to hang the mass from it. You know what, I'm going to use a heavier mass, actually. I'm going to go back to what I had here, all right? So what I've got is a mass. Notice when I put the mass on it, it stretches the spring, right? So let's stop it. Let's pretend that we stopped it at its equilibrium point. Okay, so right now this represents the point at which the force of gravity on this thing is equal to the force of the spring. Okay, that represents our relaxed position. So this is x equals 0. Okay, So let's get rid of these little arrows here, right? Okay, so right now it's not oscillating. So what I'm going to do, though, is I'm going to take it and I'm going to pull it down just a little bit and release it, and it'll oscillate up and down, all right? Now, there are two values that so you'll notice it's oscillating up and down between 2 points, right? So here's sort of the maximum point, right? I'm going to raise that up a scotch. Too far. Well, why does it mean? There we go. All right, there we go. So this is our maximum x value, right? We're going to call that xm, as in x max. All right, so it oscillates between that point and this point down here, which is the same value but negative x max, right? Oh, looks like I got to move it down a scotch. There we go. Ah, pretty good. Okay. This is still better than the one I just redid. Whoa. All right, there we go. Very good. All right, so it's oscillating between those red lines, all right? And so suppose I wanted to trace what the position was as time went on, okay? So what I might do is I might say, all right, well, so let's see. Next time it goes up through x equals 0, I'm going to start graphing. So here we go. Right? Oh, that looks like a trig function, right? This happens to be a sine curve, right? But you can definitely see that there's a trigonometric value to this, right? So that's one way I could have done this, all right? Or maybe, let's start when it's at the top. All right, you get kind of the same thing, but now it's a cosine function, right? Okay, or maybe you start when it's almost all the way up, right? And then you get, something like this, right? So you get these kind of trigonometric functions, okay? All right, now this guy here, this xm, is what's called amplitude. I will frequently just call it x max, all right? Other values we care about are the time it takes to complete one oscillation, the time it takes to go from here to here. That's called the period, all right? That's the period, okay, the time from crest to crest. And you could certainly find your frequency and your angular frequency. Your angular frequency would be 2 pi over t, okay? So there's this sort of trig feeling to this, right? Okay, so what does this look like? All right, so here's kind of the generalized version of this. All right, I'm going to skip to the next page for a minute. All right, so here we've got basically the same thing. This time, the spring is mounted horizontally, right? And there's a relaxed position, and it's going to oscillate between some maximum and minimum position. But same idea, okay? It turns out that the force of gravity here doesn't actually affect it, which is surprising. I can show you that in class if you want. And so here's our equation. All right, so it turns out if you want to write an expression for the position of the block at time t, and this also applies to the vertical example I just showed you, it can be written as your amplitude, your x max, times the cosine of this thing, which is called the phase of motion, okay? And you can see it depends on time, all right? It depends on your angular frequency. This was why it was so important that we had to have radians, okay? Because we had to write it so that we could take a trig value of it, all right? And this phi is sort of a shift to the left or the right to indicate sort of what your position is at time 0, right? Because look, if time is 0, here, so suppose we didn't have this phase constant. Suppose we didn't have that phi in there. I'm going to say phi and phi, you're going to have to deal with it. All right, so suppose that wasn't there. Well, that would mean that at time 0, cosine of 0 is 1. It would mean that at time 0, your position has to be your maximum. But that's not always the case, right? As was illustrated by, poorly, all these graphs over here, right? Your position doesn't have to start at the max. It could start somewhere else, right? And so your phi helps accomplish that, okay? And you have to figure it out. And doing so requires a pretty significant amount of care, okay? So you really got to be careful. All right. So let's make sure we've hit everything on the screen here, because I kind of went off the rails there for a minute. All right, so let's see. So here the position oscillates between your maximum and minimum values. Angular frequencies omega. Xm is the amplitude. We talked about that. This guy, this omega t plus phi, is the phase of motion. All right. The phi itself is called the phase constant, sometimes the phase angle. All right. And like I said, it kind of shifts the cosine curve to ensure the proper position at time 0. Got to be super careful. Got to be super careful. We'll do an example in a minute. Oh, and here it says, let's do an example. All right. So probably the easiest way to do this is to get a graph. All right. So I put together this kind of simple graph here. All right. All right. And so what this graph shows us is the position is on the vertical axis. It's called displacement. It's basically the position, displacement from the origin. Okay. And it gives us that as a function of time. All right. So looking at this graph, the first thing I want to do is kind of figure out the period. And this is not a great graph on a homework assignment or on an AP test. You'd probably be given a better graph. But so remember, the period is the time between the time it takes for one complete cycle. So here, that looks like it's about one complete cycle, right? And then there's another cycle. So it looks like we got 2 cycles in 10 seconds, right? Which leads me to believe that the period is, in fact, 5 seconds, right? If 2 cycles is 10 seconds, then 1 cycle is 5 seconds. All right? Ordinarily, what I would say is to find the time between identical points, so find the time from here to here. But it's a little tough to tell that on this graph, right? Or you can find the time from here to here, okay? All right, so we know our period. Oh, that means we know our frequency. Remember, it's the reciprocal, so 1/5, so that's 0.2 hertz. That means my angular frequency, well, hertz is rotations per second, so times 2 pi gives me 0.4 pi radians per second. Okay, so that's a thing I know. All right, other observations that I might make from my graph. My maximum x value is 3. I can't really tell what my starting position here is, can I? I can't really tell what my starting position is. It looks like it's somewhere between 1 and 2, but I can't tell exactly what. So I guess the only other thing I would do is, and this graph, like I said, is not great, but let's find a point on the graph where we actually know the value, okay? So it's not really, but it's close enough. Let's assume that's right there at the origin. In other words, we know that our position after 2 seconds is 0 meters, okay? I called that the origin. That's not what I meant. I meant to assume that the position is 0, okay? All right, so these are the things I know, all right? So what I want to do is I want to see if I can come up with the exact equation for this, all right? So again, the general value, or the general equation for position of a simple harmonic motion is this. Position at time t is maximum position times the cosine of omega t plus phi. Okay? And so I can plug in some of my stuff, right? So my position at time t, for us, I know my maximum position is 3 times the cosine of omega, which is 0.4 pi, times t, plus this stupid phi that I don't know. All right, so what we need to do is we need to pick phi. All right, so, or we need to find phi. We can't pick it. Sorry, we got to solve for phi. And doing so requires extra care. So what I'm going to do is I'm going to use this point right here, and I'm going to see if I can figure out what phi is. Okay, so I'm going to plug x of 2 equals 0 in. So x of 2 is 0. So x of 2 equals 0 means that 0 equals 3 times the cosine of 0.4 pi times 2 plus phi, right? So that's the same as 0 equals 3 cosine 0.8 pi plus phi. Divide by 3, that doesn't change anything, right? So let's see, where is cosine 0? Well, cosine is 0 at pi over 2 and 3 pi over 2, right? Okay, so what that means then is that 0.8 pi plus phi has got to be either pi over 2 or 3 pi over 2, right? And we got to figure out which one. All right, so to do that, what I'm going to do is I'm going to look at the velocity. Look at the velocity. All right, so let's think for a minute. So I need to ensure, look, there are a couple points here where the position is 0, right? It occurs once there where I've got the red dot, but it also occurs over here at the green dot, which is a delicious restaurant downtown. Yummy, yummy, yummy cheeseburgers and stuff. All right, so what I notice here is my slope is negative, which means my velocity is negative. Whereas over here, my slope is positive, which means my velocity is positive. And I'm guessing that one of those phase constants would give me a negative velocity, and one of those phase constants would give me a positive velocity. Okay, so let's do this. Let's think about the velocity. All right, well, look. Velocity at time t is, oh, well, that's just the derivative of the position with respect to time. So I'm going to take the derivative of this mess. So with respect to time. So time is my only variable here, right? So derivative of cosine is negative sine. I'm going to have to use the chain rule when I take that derivative and multiply by omega here. All right, so you end up getting negative xm times omega times the sine of omega t plus phi, right? And what I want to ensure is I want to ensure that my velocity after 2 seconds is in fact negative, right? So let's think about this for a minute. Here's what I know. Negative sign is negative. X max is understood to be positive. Omega is positive. So in order for this whole thing to come out negative, I need for this to be positive, right? So I need sine of omega t plus phi to be positive. So sine of omega t plus phi has to be positive. So where is phi positive? Or where is sine positive? Well, remember, I knew that this could be either pi over 2 or 3 pi over 2. And at pi over 2 is where sine is positive. At 3 pi over 2, sine is negative. So we want that phase constant, no, what was that, the phase of motion. We want this thing to be pi over 2, right? So that we get a negative times a positive times a positive. Aha. So that's got to be pi over 2. Am I doing that right? This is where I made my mistake in the video last time. I want it to be positive. Yes. So it's got to be pi over 2. So over here, it's got to be this guy. So 0.8 pi plus phi has got to equal pi over 2. Solve by subtracting 0.8 pi, and you find that phi is negative 0.3 pi. Or if you want, you can add 2 pi to that. Remember, it's cyclical, right? So you could also write it as 1.7 pi. Okay, because sine and cosine repeat themselves every 2 pi radians, right? So if you didn't want a negative phase constant, you could add 2 pi to get a positive. All right? So, holy cow, look at this. We just found out a whole bunch of stuff. Look at this. Here's what we know. We know our position at time t is 3 cosine omega, which is 0.4 pi times t minus 0.3 pi. Oh, that means the velocity at time t, if you take the derivative, remember, it's this mess, right? So you get negative, let's see, omega is 0.4 pi times 3, so that's 1.2 pi times the sine of 0.4 pi t minus 0.3 pi again. Okay? And in a minute, we're going to take another derivative to find the acceleration. All right? So holy cow, we just found a lot of stuff, didn't we? All right? A lot of trig, though, unfortunately. All right? Okay. So let's switch back to one screen here. All right. So here's kind of a summary of what we just did. All right? So simple calculus. Here's our general expression for position at time t. Taking a derivative gives our velocity at time t. Taking another derivative gives us acceleration at time t. All right. Also notice, since sine and cosine both oscillate between 1 and -1, since this is your maximum position, this must be our maximum velocity, and this must be our maximum acceleration, right? Okay, so that is totally worth noting, and it's written right here. Vm times omega xm is the maximum velocity. Am is omega squared times xm is the maximum acceleration. And in fact, notice this is just xm, right? So our acceleration is equal to negative omega squared times our position at times t. Right? Did I do that too quick? Let's scroll up. Look. I will even highlight it. Look at this. Xm cosine omega t plus 5. Xm cosine omega t plus 5. Xt. Cool. All right. And now if we multiply by the mass, look what happens. If we multiply both sides by mass, that gives us the net force, right? So net force at time t is negative omega squared m times x at times t. Oh, and remember we said that simple harmonic motion was motion in which the force was proportional to the position? Oh, here's our constant. Okay? So here we go. Here's our spring constant. Here's our constant of oscillation, m times omega squared. Okay? And so the force is negative k times position. All right? That's our simple harmonic motion. All right? So, and then you can do some quick algebra to derive this period equation, which is going to become important. So let's make sure you understand where we got that. So look, k is m omega squared, right? But remember, omega is 2 pi over t. So if you over t. So if you substitute this in here and then solve for period, it gives you this. Okay? So if you're given your spring constant, your simple harmonic constant, k, and the mass of the thing that's oscillating, you can always find the period by using this guy. All right? So this screen equals super important. Please make sure you understand everything on it. It's so important that I'm going to make sure you can see the entire page. That is too small. What's in big in it? Can I do this? Ooh, nope, too big. Maybe. Come on, smartboard. There we go. Ah! All right, so everything on this board is important right now. So put it all somewhere. As you are working through your homework, you will need every equation on this sheet. Okay? Let's clean it up a little bit. Just kind of put a finer point on it. All right, so stuff you need. Let's underline stuff you need in blue. You need this guy. 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 And 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 you need this guy. Did I just underline everything? I did. That's obnoxious. All right, well, that's a minute of your life you'll never get back. You're welcome. Or a half a minute if you're watching this and fast forward. All right, let's do an example. Oh, no. All right, I guess I should point out another thing. All right, so first of all, let me make sure you understand what this drawing is. All right, so here on the left is just sort of a stroboscope of your motion, right? So at time 0, here's my particle. All right, and then as time goes on, the particle moves left and right. Okay, so a moment later it's here, a moment later it's here, right? Okay, so it's kind of that. This is intended to represent the motion of this horizontal oscillating doohickey. Okay. And the fact that this is oscillating horizontally and the example I showed you is oscillating vertically changes literally nothing, okay? All right, so the big thing I want to make sure you understand is that the changes in your velocity are somewhat predictable, right? Because look, at your endpoints, the object stops, right? So over here, the velocity is 0. As it goes this way, it speeds up. At the center, at the equilibrium point, it hits its maximum point, its maximum velocity. Then the restoring force pulls it backwards and slows it down until it stops again. Right? Notice it stops after half of a period. Then it goes back the other way, speeds up until it gets to equilibrium. Then the restoring force slows it down, and stops it. So notice it stops twice in the period, in the course of the period, right? Notice you can't count this one and this one, just count one or the other, right? Okay. All right, and then if you rotate the figure a little bit, it gives you those waves that I was showing you before, okay? All right, so notice, and this makes sense because you know calculus, right? Remember, the derivative here is 0, which means the velocity here and here are 0, right? Okay, and the speed is the greatest at these points because that's where your slope is the greatest, right? Okay. All righty. So let's talk about how these graphs are different. So we got a red graph and a blue graph. We're going to ignore the fact that the red is really pink. All right, so what's the difference here? What's the difference between those two graphs? Well, they're the same, except they have different x-maxes, right? Okay, the only difference between these two graphs is the x-max for the red graph is greater than the x-max for the blue graph. Okay, that little prime there is not meant to indicate a derivative. It's just meant to indicate a different x-max. So there's two x-maxes here, x-max and x-max prime. They're just different names for different points. Okay, so everything else about these are the same. They have the same period, same frequency, same angular frequency. The only difference is the amplitude. The amplitude of the red graph is bigger than the blue one. Okay, over here, looking at graph B, they have the same maximum. They have the same amplitude, but they have different periods, right? So now we've got the period for the blue graph is this, and the period for the red graph is this, right? So now the period is greater than the period. Okay? All right? And then down here at the bottom, so here, everything about these graphs is the same, except for the periods. Finally, this last graph, graph C over here, everything is the same except for the phase constant, right? Please notice the blue graph, you don't need to figure this out mathematically. You can figure out that your phi is 0 because when you graph cosine, cosine of 0 is 1. So anytime your graph starts at a max, that implies that your phi is 0. Okay? Whereas with the red graph, it's been shifted over pi over 4 radians, okay? Notice a negative phase constant implies a shift to the right, okay? And that's actually maybe an easier way that we, well, I guess, yeah, you don't know how far it got shifted, so maybe that's not the best way to do it. Okay, so anyway, so it's shifted to the right, pi over 4 radians. Okay? Do I agree with that? I think I do. Let's go back over here. What did we get? Sorry, now you gotta wait while I think for a minute. So we figured out that our phi was 0.3 pi. 0.3 pi is about 1. How far did this get shifted? It got shifted to the right. About 1. Okay, yeah, I guess that works, right? Here we got shifted to the right about 1, which is the same as 0.3 pi, right? Ballpark? A little more than 1. I guess that's maybe an easy way to think about it. Cool. You learn stuff so much better when you teach it, even if you're just talking to a board. It's weird. All right, let's do an example. Let's do a real live oh no. Whew. You should pause it and go get yourself a soda. We can't split this up into 2 videos because otherwise the next example won't make any sense. All right, let's talk about energy. So the idea is when your thing is oscillating, look what's happening. Let's go back to this little video over here. So look, what's happening is, and let's get rid of all of our ink over here. All right, so the idea is this thing is oscillating between, at the end point here, all of your energy is elastic potential energy. Okay, at the very center, it's at its equilibrium point, so there's sort of no elastic potential energy. Up here at the top, again, there's elastic potential energy because now your spring is squished from your equilibrium point, right? So the idea is, at these two endpoints, what's going on? Your kinetic energy here is 0, your kinetic energy here is 0. Down here, you can treat your elastic potential energy as being 0, which means that the elastic potential energy here is, let's give it a name. How about smiley face? Oh, well, that means the kinetic energy here must be that same smiley face, right? In order for your energy to be conserved, right? Okay, so you're basically just oscillating between elastic and kinetic energy, okay? Now, I will say this is a little bit sloppy in this particular example because your EPE here is not technically 0. But weirdly, you can treat it as 0. I'll have to talk about why that's true in class. I guess my point is it doesn't change any of what I've just kind of explained here. Okay. All right, so back to this. How are we doing on time? I'm at like 7 hours, aren't I? Yeah. All right. Okay, so let's look at our graphs. All right, so here, this graph right here, let's embiggen this so you can see it a little better. All right, so this top graph is position as a function of time. Taking the derivative gives us this velocity as a function of time graph, okay? And it should make sense, right? Velocity 0 corresponds to velocity of 0. Maximum negative velocity corresponds to maximum negative velocity. Velocity is 0, velocity is 0. Maximum positive velocity, maximum positive velocity. Okay? Right? Because this is the maximum positive slope right there. That's why it's maximum velocity. Okay? So if I take this top graph and do 1/2 kx squared, basically what it's going to do is it's going to, well, A, it'll give us our elastic potential energy equation, right? And what it's going to do is it's going to give us a graph that looks, I wish I had a little more room. All right, so if you graph u as a function of x, let's see, got our little dotted lines, let's extend those dotted lines down. All right, so let's see, this blue dot up here corresponds to our maximum x, therefore our maximum elastic potential energy. At the green dot, our x is 0, which means our elastic potential energy is 0. At the red x, well, it's x is squared, so the fact that x is negative doesn't matter. So that's going to put us back up here again, right? And then we go back down to 0 again, right? X is 0 at the black x is 0 at the black, right? So my elastic potential energy function looks like this. Okay, it turns out to be a cosine graph that's shifted up, and the frequency is doubled. It happens twice as often, right? Okay. All right, now if we repeat the same process with our kinetic energy and our velocity, you get kind of the same idea. So let's do kinetic energy. Okay, so let's see, the blue dot corresponds to a velocity of 0, that's a kinetic energy of 0. The green dot is our maximum negative velocity, that means our maximum kinetic energy. The negative doesn't matter because it gets squared out. All right, at the red x, our velocity is 0. At the black x, our velocity is at its maximum again, positive now, right? Okay, and so now here's my graph. All right. And for one awesomeness point, what would you get if you added u and k? Right? Because your total energy ought to be constant. Okay. So remember, your total energy is either your maximum kinetic energy or your maximum elastic potential energy. All right? So let's do an example. Here we go. All right, you know what? I'm going to pause because I need a drink of water. All right, so here we go. Kabam, and big in, there we go. All right, so we got this graph at the right. It gives the position of a 20-gram block. Do you know what I want to do? Hang on one second. Well, here, I'll leave this up here for a minute. Take a second, make a note, maybe sketch the graph real quick. I want to put the equations up on the board. All right, I guess I can do this. All right, so here's what we know. We know the mass of our block is 0.02 kilograms. We know that the time over here is 0.04 seconds. 40 milliseconds is the way it's written, okay? So that means this must be 0.02, etc. So let's write that down. Capital T for period is 0.04 seconds. If you do 1 over that, your frequency turns out to be 25 hertz. Times 2 pi, your angular frequency is 50 pi radians per second. All right. All right, so question A wants us to find the maximum kinetic energy of the block. All right, there are a bunch of ways we can do this. All right, and I'm down here, in fact, question E says there's 2 ways to do this. So we're going to do it both ways. All right, so the first way I'm going to do it is by kind of doing the same sort of process we did a minute ago, which is as follows. Let's write an expression for the position, then find the velocity. All right, so let's see. Here's what I know. Oh, wait, we don't even need to do that. All right, let's do this. Boom, close that guy. Let's go over to here. Remember I told you these equations were super important? Let's lock those. Pin those down. Kabam! Maybe? Pin? Oh, no. To screen. Over here. Boom. Pin it. There we go. Now we can go over to the end. Nope, too far. There we go. Okay, so find the maximum kinetic energy. Well, the maximum kinetic energy is 1/2 mv squared, but we want the maximum velocity, right? Oh, well, remember, over here in teeny tiny little letters, we learned that our maximum velocity was omega times xm. So V max is omega times xm. So let's see. Omega is 50 pi. xm, according to our graph, I did not write it down. I'm going to go back over here. We know that x max is 7 centimeters, 0.07 meters. That's just from the graph over here. You can tell that maximum point is 7. Okay, so times 7, no, not times 7, times 0.07 meters, and that gives you 3.5 pi meters per second. Now I can find my KE max by plugging in 1/2 the mass times the velocity. Don't forget to square it. And it gives you pretty close to 1.2 joules. I think it's a scotch more. Right, so that's part A. Part B, how many times per second do you reach the maximum velocity? Well, it happens twice per period, right? Twice per period. So it happens once here and once here, right? So you have 25 cycles per second, so double that is 50 times per second. Okay, so you reach that maximum 50 times per second. All right, question C wants to know the spring constant. Question C wants to know the spring constant. Oh, well, the spring constant is m omega squared. All right, so our mass is 0.02 kilograms. Omega is 50 pi. Radians per second. Don't forget to square it. Multiply it. And it gives you pretty close to 394. No, it doesn't. 494 newtons per meter. Convince yourself that that's newtons per meter. You can do the dimensional analysis on your own. I'm already going real long here. All right, let's see what we got now. Whoa. Hello. Why won't you? It won't let me scroll up. That is annoying. All right, question D. Find the velocity when you're at a position of 4 centimeters. Ugh. All right. Well, let's see. I guess I gotta exit dual page here, unfortunately. Thank you for being patient, as I assume you're being patient. I don't know, maybe you're throwing stuff at your screen. I don't know what you're doing at home. Okay, so we got to find the velocity at a position of 4 centimeters. Well, so let's find our position equation. So position at time t is xm cosine omega t plus phi. So let's see, our x max is 0.07 times cosine of omega is 50 pi times t plus phi. Ugh, we got to find phi. But, oh, not ugh. Notice it starts at a max, right? It starts at a max. So that means phi is 0. That was what we learned, right? Anytime you start at a positive max, your phi is 0. If you start at a negative max, your phi is pi. Okay. Oh, that's that. Oh, cool. Now I can find v of t because it's just the derivative of that, right? So negative, let's see, we got to multiply 0.07 times 50 pi, right? Chain rule. So that gives you 3.5 pi cosine, nope, sine, sorry. Take our derivative, gives us sine of 50 pi times t. So now I can plug in my time. What's the velocity when it's at a position of 4? Ugh. I gotta find the time, don't I? All right, so x of t, oops, equals 4. No, it doesn't. It equals 0.04. I feel like I just did this. I don't remember doing that. No, I see. It's because I didn't do it. All right, so we got to find our time. So that's equal to 0.07 cosine 50 pi times t. So divide both sides by 0.07, and you get 4/7 equals cosine of 50 pi times t. Inverse cosine, and you will find, I guess we're going to have to do a little bit of looking at our graph here, right? So let me grab my calculator. So 4/7 is about a half. So we're looking at either here or maybe down here, right? Oh, I guess it doesn't matter, right? Why? We're trying to find the velocity when it's at a position of 4, right? So that happens twice. Once with a positive velocity, once with a negative velocity. So it doesn't really matter which one we pick, right? So we can just solve it. All right, so I'm going to do inverse cosine of both sides. Second cosine of 4 divided by 7. So now I'm looking at 50 pi times t equals, my calculator is in degrees, I need it to be in radians. This is going to be annoying, I'm going to forget that I did that later on. It gives you 0.963. So now divide by 50 pi. So divided by, in parentheses, 50 pi. And you get a syntax error. Oh, it's because I used the wrong kind of parentheses. There we go. So 0.006 seconds. So now I can plug that in up here and find my velocity. So that times 50 pi, sine of it, times 3.5 pi, I'm going to not worry about the negative. So you're going to get V equals positive or negative 9 meters per second. Yeesh. Okay, so that worked. It was kind of a hassle, and maybe that provides extra fodder. That's not the word I want. Extra emphasis, extra reasoning why knowing both methods is useful. Here's what I'm going to do. Let's go back and do that again. All right, so we already figured out a whole bunch of stuff over here in parts A, B, and C, right? Let's do this. We know our total energy is constant. In fact, our total energy has got to equal our maximum kinetic energy, right? So let's do this. Let's find our elastic potential energy at x equals 0.04. Oh, well, elastic potential energy is 1/2 kx squared, right? So that's 1/2 k, we found in part C, it was 494 times x, which is 0.04. Don't forget to square it. Solve that, and you get an elastic potential energy of, turns out to be pretty close to 0.4 joules. It's actually like 0.395. Okay. Oh, well then that means my kinetic energy has got to be 1.2 minus 0.4. So 0.8 joules. So if KE is 1/2 mv squared, I know my KE, I know my mass, I can solve for the velocity. That also gives you 9 meters per second. That way is definitely easier, and there's value in knowing how to do it both ways. All right. That is it. I got to skedaddle.